In today's lesson, we are going to start learning about kinetic molecular theory. This has to do with how gases work in relation to number of moles, or the molecules of gas, temperature, volume, and pressure. As always, I ask that you would watch this video on either your phone or computer, so that way you can take notes as you follow along on your iPad. Here's a quick overview of the difference between a solid, liquid, and gas. So keep in mind, in this unit we are going to be talking primarily about gases. However, remember, a solid is something that has a definite shape and a definite volume. And you can picture this with any other solid. And what's happening in a solid is that all of the molecules are very, very compact, as you can see here. They're all very close together. And they have a relatively high density. In a liquid, they have no definite shape. And you can picture this: if you take water from one glass and pour it into a bottle, it's going to take the shape of that container. It does have a definite volume, so if you pour 25 milliliters from a glass and then pour it into a bottle, you're still going to have 25 milliliters. And for the most part, liquids don't compress very much either. They're still pretty compact, not as much as a solid, but the molecules are able to slide over one another, so they're a little bit more spread out and they don't have as much structure as a solid does. But what we're really focusing on in this unit is gases, and you'll notice gases represented in each one of these little dots represents a molecule. They're flying all over the place, as you can see by these trails, so they're just kind of bouncing all over the walls of their container. So they have no definite shape, they don't have a definite volume, and what that means is, if you think about, like, if you're holding a balloon, you can take that balloon in your hand and squeeze it, and you're changing the volume of it. And you also would be changing the shape. And hence they are compressible. When you squeeze that balloon, you are compressing it, you are pushing those molecules closer and closer together. And that is because in a gas, there's a ton of room between all of the molecules, as you can see in this picture. So when you're squeezing something, you're just pushing those molecules closer together, and they start to fill in that empty space. So what kinetic molecular theory, often referred to as KMT, does is it describes the behavior of gases. When we talk about kinetic molecular theory in this general chemistry course, we are going to make some assumptions. So in here we're talking about what's called an ideal gas, whereas in a perfect world this is how gases would react. However, in real life, those are real gases and their properties are a little bit different, but for the sake of simplifying things a little bit, we are going to assume that these are ideal gases. So one assumption that we make is that particle size are so small compared to the amount of empty space that we don't really worry about the size of the particle. And when I talk about size of the particle, that is like if you think of, say, helium. Well, helium is a very, very small gas. And that would be like, if a helium was the size of this little green dot there. And now we look at a much larger gas, such as xenon or radon or something like that. Well, the size of that particle is going to be larger. So we're just saying that compared to the huge amount of space in gases, the particle size is very, very small. A couple things to keep in mind, and we'll keep referencing back to this, is that your 1 mole has 6.02 times 10 to the 23rd particles. Doesn't matter, it could be of oxygen or helium. That is just the number of atoms or molecules in 1 mole. Also remember, this is what's called Avogadro's number. And then 1 mole of any ideal gas is going to occupy 22.4 liters. So picture, like 11 2-liter bottles. And there's my drawing of a bottle. So picture 11 of those. Well, 1 mole of gas is going to take up about 11 2-liter bottles at standard temperature, and we consider standard temperature to be 0 degrees Celsius, which is the temperature that water freezes at. Typical room that you're sitting in is about 25 degrees Celsius. And then we also assume at 1 atmosphere of pressure, which is just basically at sea level. Now what this means, and the reason that these are all considered basically what we call STP, or standard temperature pressure, is as I change pressure, my volume would change. or as I change the volume, my pressure would change, or as I change temperature, my volume and pressure would both change. So the only way that this works is if all four of these standards are met. Is if we have exactly 1 mole of gas, it will take up 22.4 liters of space at exactly 0 degrees Celsius and 1 atmosphere of pressure. Another thing that we assume with kinetic molecular theory is particle motion. So we are assuming that gases are in constant random motion. They are going all over the place. However, when we say random, we are assuming that they move in a straight line until they collide with something else. For example, if here I have a wall, and then I have this particle, well, if that particle is moving, what's going to happen is it's always moving in a straight line until it hits something else. So here it hits, and is going to bounce off at a 90-degree angle. It's going to continue on that same path. And what pressure is in anything. So now if I take and I'm just going to erase this drawing really quick. And if I draw, say, a balloon, so here's my balloon, and in there I have all of these gas particles floating around. Well, what pressure is this gas particle here is flying and hitting the walls of the container and flying all over and just keeps hitting walls of the container and ends up all over the place. And you have all of these particles that are doing that. They're flying all over the place and hitting the walls of the container. As they hit those walls, they're exerting a force on it and they're pushing that outwards. And that's what pressure is. We also assume that collisions are elastic. That is, that when these particles hit the walls of that container, they are bouncing back with the same velocity that they hit the wall with. So they're not losing any of their energy to the wall. Again, this is in what we call an ideal gas, not necessarily in the real world. And then we say that average kinetic energy, or the rate of movement, is directly related to temperature. Because remember, temperature, or when you record a temperature, you are essentially measuring the speed of the molecules. As temperature increases, as you heat something up, the molecules are moving faster and faster and faster and faster and faster. This slide deals with particle energy, where here we say the kinetic energy, or that is essentially like the moving energy of any particle, is equal to 1/2 its mass, so that M does stand for mass, times its velocity, that is not standing for volume in this case, it's standing for velocity, squared. So kinetic energy equals 1/2 mass velocity squared. Molecules of the same gas have the same mass but can have different velocities at a given temperature. What this means is that if we have a container and I record the temperature of it, so I stick my thermometer in there and I record the temperature of this. Well, what's happening is some of the molecules are moving slowly and some of them are going to be moving faster and some are moving even faster and faster. But what you're doing when you take temperature is it's finding the average of all of those particles. So any one given particle can have a relatively low velocity, but the average of them kind of evens out, and then some of the particles are going to have a very, very high velocity. But when you're taking the temperature, you're kind of finding the average of all of the particles in there. And one of the last assumptions that we make about ideal gases is that the attractive force between them is completely negligible. What that means is we are assuming that if particles are flying by one another, so here I have one particle, and then I have another particle, and this particle is flying past this one, I am going to assume that it is not attracted to this black particle at all. It doesn't loop around, when in reality, it might cause it to loop a little bit because they're attracted to one another. But in here, we are going to assume that particles have no attraction between one another, and they will just keep flying in the direction that they were going. We also make another assumption that the particles, if they're moving and they hit one another, same as I talked about the wall, so they do actually end up colliding, then they will affect each other. And we are assuming that their collisions are elastic, so they bounce away from each other with the same speed that they hit with. So no energy is lost in the collision. Same as I talked about when the molecules hit the wall. So there are 4 factors that affect kinetic molecular theory. And we talked about this a few slides ago when I told you about moles and liters and things like that. So the number of gas particles, and this is going to be represented by N in this unit. And 1 mole is equal to 22.4 liters at standard temperature and pressure. Temperature, we are going to always want to use the unit of Kelvin in this case, and this might be a new unit to some of you. So what Kelvin is it is degrees Celsius plus 273. So that means if I gave you 25 degrees Celsius and I told you to find the temperature in Kelvin, you would just take that plus 273, and that would mean that the temperature in Kelvin is 298. In Kelvin, we don't write the degree symbol, it is just called 298 Kelvin. And the reason that we use Kelvin is because when we talk about the theoretical point of absolute zero, that is the absolute coldest temperature possible. That is when molecules would have no energy. Molecules would literally be sitting still. That is 0 degrees Kelvin. And that's why we have the Kelvin scale. Another thing to remember is that pressure is created by the particles or the molecules hitting the walls of the container. And there's going to be a few different units that we use in this unit. So one is called the ATM, one is millimeters of mercury, one is kilopascals, and another is PSI, which you're probably more familiar with than any of the others. So 1 ATM is equal to 760 millimeters of mercury, which is equal to 103.1 kilopascals, which is equal to 14.3 pounds per square inch. They're just different units. So 1 ATM again is the atmospheric pressure, which we take at sea level, and we're saying the pressure weighing down of all of the air acting on you is considered to be 1 ATM. And another thing to keep in mind with pressure is gases will move from areas of high pressure to areas of low pressure. A good example of this is if you're into the weather at all, you will often see that if you're in your town or whatever, and then there is a low pressure system in your area, well, high pressure is going to move in, and that's what causes storms and wind. So the pressure falls into the area of low pressure. You can also think about this like a bathtub drain. So in your bathtub, you have it filled up, and then you have your drain. Well, in your bathtub you have all of your water in there, and when your drain is open, that water wants to flow from the high pressure, where you have a lot more of that, to the empty space down here. Now, if that drain is completely clogged, or if it's filled with water, your water doesn't drain out of your bathtub because there's no lower pressure area to go to. So it's going to just sit there. So that's just one thing to keep in mind, is that gases are going to flow from high pressure to areas of low pressure. And then last factor that we use in this unit is going to be volume. And that is just going to be the size of an object, and we often refer to that in liters or milliliters. For those of you just watching the video lesson, I do a can crushing demo in class. You can visit this YouTube link if you would like to see what's happening, but I will just quickly explain what is happening in can crushing demo. So in the demo, I have a can, and it is being heated up on a hot plate. And so, I don't know, I might heat it at 200 degrees Celsius or so. And what I'm doing in this can is I actually add a little bit of water, just enough to kind of cover the bottom of the can, and we heat that up. Well, as we heat something, or as we heat that water, it is going from the liquid phase into a gas phase. And what's going to happen is, as this goes into the gas phase, these water molecules are going to force out all of the air. So all of the air that was in there, not all of it, but a lot of that air is going to be forced out. And then, once this water is hot enough, I have a tub full of cool water, and this even works with just room temperature water, and this is just filled with water. And what happens is I pick the can up, and upside down, I flip it into the cool water. So what's going to happen when all of these gas molecules, all of these water molecules are suddenly cooled down? And there's nowhere for air to get sucked in because the top of the can here, the opening of the can, is now upside down in the water. Well, all of these water molecules are going to cool down. So these are all going to cool down, and they are going to turn back into water. Well, as they condense back into water, now we have all of this empty space up in the can. And this empty space creates a vacuum. There's no more pressure. There's not as many molecules now hitting the walls of this container. So what happens is you end up with this can that is crushed. It's caved in because it is no longer it no longer has enough pressure, no longer has enough molecules in there to keep the walls of the container pushed out. So to show you this again, here we have our can, and as those water molecules cool down and we don't have as many molecules, we only have a couple molecules in here hitting the walls of this container, we still have all of these molecules hitting the outside of the container from our atmospheric pressure. And so all of those molecules are now stronger than the few that are on the inside, and so that can is going to concave and be crushed in. Again, a link has been provided to you if you want to watch a demo of this, but what is happening in this demo is we have a balloon, and the balloon has been tied off, and it is placed into what is called a vacuum chamber. So in the vacuum chamber, we're going to start off and we're going to start sucking all of the air molecules out of the chamber. Well, as all of these air molecules, so I'm going to draw in some air molecules quick, and we also have air molecules inside of the balloon, and these molecules are all battling against each other. The ones on the outside are pushing against the ones on the inside, and so they're in this constant struggle. Well, as we suck all of the air out of this, and now all the molecules that are inside of this vacuum chamber are being lost, suddenly the molecules on the inside are able to, they're winning that battle. And so this balloon is actually going to start to expand. So this balloon is going to get larger and larger and larger. And then that is a good relationship of pressure versus volume. As the pressure on the outside decreased and the pressure on the inside increased, the volume of the balloon expanded. We can also do the reverse of this. Instead of sucking air out of the vacuum chamber, we can actually push a bunch of air back into it. So as we increase and get just a ton more molecules on the outside, well, now the molecules on the outside of the balloon are going to start winning the battle compared to the ones on the inside. And so this balloon is going to, and sorry, I'm going to have to draw this as a different color. Now this balloon is going to shrink and be very, very small because all of these molecules that are on the outside are compressing it. And we can also use kinetic molecular theory to talk about the air pressure in your tires during the winter. So during the summer you have your car tire, and in there you have all of these molecules flying around. And they are exerting a pressure on the walls of your tire by running into it. Well, during the winter, as temperature drops, remember temperature is a measure of the speed of the molecules, so as the molecules slow down, they're not hitting the walls of the container with as much velocity, so their kinetic energy is lower, and therefore the volume in your tire actually shrinks during the winter. And that is why when the winter comes, the pressure in your tire decreases, is because the molecules don't have as much speed, so they're not hitting the walls of the container as hard. The way that we, I guess you could say, counteract that is we will put more air into our tires. So as we increase the number of molecules, now these molecules are able to hit the walls of the container with more force. Or not more force, but there are more molecules hitting the wall of the container. And then one more thing just to kind of finish up with the properties of gases. They are very compressible. So what that means is because there's so much empty space in any container, you know, you have all these molecules and there's just a ton of empty space in there, you are able to compress these molecules together. They're just going to get closer and closer together. Gases have a very low density, and again, that's because there's so much space between them. They are able to be expanded, so you can take, say, a balloon and you can actually stretch it out. You're just increasing the volume. Now you're increasing the space between all of the particles, And another thing to keep in mind is gases are considered a fluid. That is because they will slide or move past one another smoothly.